Okay, we're back with another exam walkthrough. This is going to be the continuation of our 2024 June Unit 2. We're going to be going through question number 14 and question number 16. Okay, and you can try out the questions I'm going to show on the screen right now. So first is this question. You can pause the video and try it out. The next question is this one. And the last question, the last question is this one. And if you want to see the mark scheme and the examiner report, you can go to the end of the video. And if you want to see my solutions and how I solve it, then you can just stick around. Okay, so it says an electrical heating system consists of heating panels, and each panel is made of thin sheet of conducting material attached to two copper electrodes. So you have those two copper electrodes, and then you have the conducting material. The electrodes are connected to a power supply. Okay, and then it says a student uses a sample of conducting material to determine its resistivity, and you have to state what is meant by resistivity of a material. So we know resistance is equals to rho L over A, and the rho is resistivity, and if we make rho the subject, we get R times A over L will give us rho. So here's the definition. It's the resistance of the sample, unit cross-sectional area, and unit length. That's the definition. I will show one more definition as well that you can write, but this is the definition that's there in the mark scheme, and it's the first one that they've given. You can also mention an alternative one, which I will show you just now. So here's the other one that you can write: resistance of a sample, or resistance, I think it's better, right? Resistance of the sample times the cross-sectional area and per unit length. Okay, the main thing that they're looking for here, one of the key things, is that you mention cross-sectional area instead of just area. So this definition will also get you the 1 mark, and the one that I wrote will also get you the 1 mark. Okay, so let's move on. Next part, describe how the student could determine a value for the resistivity of the conducting material. So for this one, you need to refer to the core practical that's there. So it is kind of like connected to the core practical. Okay, so we have to determine the resistivity of the conducting material. So again, let's stick to the formula. So I need resistance, I need area, and I need length to find the resistivity. So first off, you're going to measure the length using a meter rule. Now to find the area, okay, what we need to do is we need to determine two things. We need to determine the thickness and the and the width. Okay, so we need to determine these two to get the area. Okay, this is not going to be a wire, so there is no point in finding the radius. So you're gonna find the thickness and the width using either you can use a micrometer or you can use vernier calipers as well. So we're going to measure the thickness and width using micrometer and do thickness times width to get the area. Okay, so we have found the length, we have done thickness times width to get the area, and now we can use an ohmmeter to determine the resistance. You can also use obviously a voltmeter in parallel to find the voltage, and then you can use an ammeter in series to get your values of voltage and current, and then you can do V is equals to IR and B over I is equals to R to get the resistance as well. That's totally valid. Okay, and then you're going to use the formula rho is equals to R A over L. So you can use this formula. Another thing you can do is you can also use a graph. So you can use the graph of R is equals to rho L over A. Okay, and what you can do is you can vary the length, and because the length will vary, the resistance will also vary, varying resistance. Okay, or I try change resistance. Changes resistance. Okay, so vary the length, resistance will change. and the constant are these two. So you can, R is equals to rho over A, L, Y is equals to mx. So here you have a straight line, this is L, this is R, and then you get the gradient as rho over A, and gradient times the area will give you the value of resistivity. Okay, so you'll get 1 mark for this or 1 mark for this, depends which one you mention. 1 mark for this, 1 mark for this, and 1 mark for this. Okay, so that's clear. Now let's move on to the next part. Let me just move it a bit down. Okay. It says copper has a low resistivity compared with the resistivity of the conducting material. Okay. Explain how the low resistivity of copper affects the drift velocity of the electrons. So remember, we talked about 3 materials in the class. We talked about insulators, semiconductors, and conductors. The conductors have the lowest value of resistivity. Semiconductors kind of fall in the middle, and then your insulators have the highest conductivity value. And the reason for all of these is because the concentration of charges, or the value of n here, the charge density, okay, the charge density of the number of charge carriers, okay, is going to be the highest in conductors and the lowest in insulators. Alright, so we can connect that to this. We can say that copper has low resistivity compared with the resistivity of a conducting material. So copper has lower resistivity than even conductors, which means that it really has a lot of electrons, right? So we can say copper has a high concentration of charge carriers. Now for a given current, which means the current is constant, for a given current, we have NQVA. For a given current, if our N, which is the concentration of charge carriers, is going to be high, then our drift velocity will be less. So so our drift velocity is smaller. Okay, that's going to be 1 mark for this and 1 mark for this. Okay, now let's move on to the next part. It says the power output of the heating system can be changed by connecting more panels in parallel with the power supply as shown. Okay, I want to highlight 2 things here. Remember, when things are connected in parallel, the potential difference across them is going to be the same. Okay, so across all of these, the potential difference will be the same. The next thing, when things are connected in parallel, the overall effective or the total resistance is going to go down. So when you connect things in parallel, the total resistance is going to go down. Okay, so number 1, the resistance goes down and the voltage across all of them is going to be the same. So here are the 2 points. I've written them in the context. The PD across the heating panel is the same, and then the total resistance of the system of panels decreases. So PD across each of the panels is going to remain the same, and the overall or the total resistance of the system will decrease. And we can say that P is equals to V square over R. So if our resistance decreases, our power output should increase. So our power output should increase. Okay, so hope all of these make sense. You can just go through them. Okay, we have a really good 5 marker here. So it says a student designs a heating system using 5 heating panels as shown. And then it says to be safe, the maximum power of the student's heating system should be less than 350 watts. Deduce whether this is correct. So they've given me all the values here. And actually, I have to connect this with the previous question. So previous question, we used this formula to find the power output. And then here also it's talking about the maximum power. It's talking about the power output, right? And we have to see if the power output is greater than this or less than this and compare. So I can just use the formula P is equals to V square over the total resistance. So I want to find the total resistance of all of these. which means I have to find the resistance of one of these. And to find the resistance, I can see they give me resistivity, thickness, and they've given me the length and the width as well. So what I can do here is I can do R is equals to rho L over A. Now, how do we find one second. How do we find the length here? So the length, is it this one or is it this one? Well, that's quite simple. All you have to understand is when the electrons are going to flow. So, or the current, when the current flows, it's going to move like this, it's going to move like this, and they're going to move like this. So this is the length they travel, and then they go back again. Okay, so this is the length that they're going to travel, 51 centimeter. Okay, and then this is going to be the cross-sectional area. Okay, it's going to look something like this. So you're going to have this, and you're going to have this electrode. So this is going to be one electrode, this is going to be the other electrode. The electrons are going to come like, one second, the electrons are going to come like this. They're going to enter through this and go like this. Okay, so they're going to go like this. This is going to be the cross-sectional area, and this is going to be the length L. Cross-sectional area is going to be the width times the thickness. So it's going to be thickness, this is going to be the width, and that's going to be the length right over there, which is 51 centimeter. This is going to be 0.48. This is going to be 1.6. Okay, so then you can plug all the values into this formula. So this was something that sometimes students find difficult to get the hang of. Okay, so it's good to trace how the current goes and understand it. So I've plugged in the values and we'll get 4.25 ohms as the answer. So we have 1, 2, 3, 4, 5. So we have 5 of them connected in parallel to each other. So what we can do is we can say 1 over R total is going to be 1 over 4.25 plus 1 over 4.25 plus 1 over 4.25. Give me a second. Plus 1 over 4.25. We're going to do this 5 times. 1, 2, 3, 4, 5. 1, 2, 3, 4, and then plus 4.25. Now you can do all of this. You can add all of them, and then you can flip both sides. Okay, and then you get the answer. There's an easier way to do this as well. Okay, the easier way is that since all of them have the same resistance, so we have 5 identical resistors that are connected in parallel. If you have 5 identical resistors connected in parallel, then your total resistance will be the resistance of one of them divided by the number of resistors. And if it's series, then the total resistance will be N times R, where N is the number of resistors, identical resistors, and R is the resistance of one of them. So here is the resistance of all of them together. Now this is only if you have identical resistors. If you didn't have, if all of them had different resistances, you have to do it the usual way we do it. Okay, and then we have the potential difference across them as 24. So we'll do 24 square over 0.85. So that's going to give me 678 watts, which is obviously greater than 350 watts, so it is not safe. So I was going to put in another question, but this video is kind of long already. So I'm going to make another video on question number 16. I'm going to show you the mark scheme and the examiner report, and then we'll end the video.